One more quick example to show you the power of this. It'll look almost identical to example 1. You're given this problem. What you want to do is recognize that part of this thing, this x to the 10th, has its derivative, x to the 9th, within the problem as well. And you're like, wait, the derivative of x to the 10th is not x to the 9th, it's 10x to the 9th. That's true. I don't need the exact derivative of that part in here. I can be off by a constant. And I'll show you how you can be off by a constant. So even though the derivative is really 10x to the 9th, this x to the 9th will be the important part of the derivative to show up. This will end up being a u substitution problem. You're given this problem, and what you want to be able to do is recognize that u should be equal to x to the 10th power. And for most people, that's the hardest part of u substitution, is determining what the substitution should be. A big challenge with calculus 2 that you start to see in this section that you haven't seen before is problems are less about following a series of defined steps and more about a puzzle that you need to solve. And often the best method of attack is just play with it for a little while. See if you can get anywhere. Expect yourself to try methods that won't work. Anyways, let's let u equal x to the 10th power. What's your next step the minute you determine that u is x to the 10th power? Well, we're going to need to know the derivative. Du over dx is the symbol I've been using for u, is 10x to the 9th power. Oh, but now all of a sudden I can treat this as a fraction and just say that du is 10x to the 9th times dx. I can multiply both sides of the equation by dx. It's worth pointing out that probably by the time we start the next video, you're going to go straight from here to here. You're not going to bother writing this step. You're going to be like, u is x to the 10th, so du is 10x to the 9th dx. Du will kind of stand for the derivative of this thing u, but you'll have to remember to put the dx over on the other side. And be like, why is the dx on the other side? Well, du over dx is the symbol that we use for the derivative of u. Anyways, you get this far. There's a problem. We don't have a 10x to the 9th dx up in this expression here. We have an x to the 9th times dx in this expression, but not a 10x to the 9th dx. No problem. This is an equation. Multiply both sides by 1/10. A tenth of du is x to the 9th dx. I didn't need the entire 10x to the 9th, the derivative of this thing u, to appear in here. I could be off by a constant because I can make up for that constant down here, dividing both sides by 10, or multiplying by a tenth. Now I can do my substitutions. Coming back up here, I'm taking the integral of the sine of x to the 10th. Well, the x to the 10th changes into a u, so I got the sine of u here. Oh, but you still have the x to the 9th and the dx here. Right, but x to the 9th and dx changes into 1/10 du. Maybe I'll write it here just so you can follow where all the pieces go. But note, this is the sine of u times 1/10. Wait, you're multiplying by a constant. I thought when you multiply by a constant, you could just pull that constant out in front of the integral. Absolutely you can. This is just 1/10 the integral of sine of u du. The integral of sine of u du, that's easy. That's just the negative cosine of u plus some constant. And then u is just x to the 10th power. This whole thing, I can just call it negative 1/10 cosine of x to the 10th plus c. And I got my answer. Like everything else we do in this class, when you get this far, if you're not sure if you did things right, no problem, just go back and check it. Take the derivative of this guy. Take the derivative of this guy, I'm pretty sure you'll get this as your answer, and that will justify this method of u substitution in the first place.